Hello, it's Stephen Neshaban. I'm here to help you out with the computational guided inquiry on climate modeling. So here's the handout for that, and here's the figure one, which kind of just shows you the basic idea. We've got short wave coming in from the sun, got long wave coming off the earth, and when those two are in balance, equal to each other, then we're in radiative balance, and what controls this long wave is what the temperature of the Earth is. The higher the temperature of the Earth is, the more long wave, and so that's a mechanism by which the Earth will find its own proper temperature. Now that's kind of given graphically right here. You imagine that as the temperature of the Earth's surface goes up, the long wave radiance coming off it follows this blue curve, which is the Stefan-Boltzmann curve, and here this dash red curve is the radiance coming in, and that's just constant. That's the amount of energy that the Earth intercepts from the sun. So it's somewhere around 250, where they are obviously in balance. And so in terms of formulas, what we got here is I1. That's the outgoing. That's the incoming dash curve here. Solar constant times a factor about the albedo times pi r squared. That's target area. And then what's going out, this blue curve here is given by I2. That's a Stefan-Boltzmann formula, sigma t to the fourth times the surface area of the planet. And so we're looking for where those are equal. Now, therefore, the condition of radiative balance will be that I1 equals I2. And you can see that there's a pi r squared factor common in both of those. So what really we're looking for is where this part here, S naught times 1 minus alpha, is equal to sigma t to the fourth times 4. So next thing to do is to go to Excel and launch, through VDesk, launch Excel. And what I recommend is you enter in all these fields here, and just so you're all ready to go when we start entering some numbers. So pause and then resume when you got that up. Okay, now assuming you got that up, well, what we're going to first do is just enter some numbers. So here's S naught. There's a box for S naught, so that's 1367, and I'm just going to enter that. Albedo, that's 0.3. Fine, I can do that. Now sigma is a number that is best entered in scientific notation here, and let me show you how to do that. We go 5.67, and then E minus 8. That stands for 10 to the minus 8. So I'm going to hit return there. Now the temperature here, we can make a guess. It's somewhere around 250. I'm just going to type in 200 for just have something to start with there, because we're going to have Excel find that number for us the best. Okay, now I have two fields here ready to enter in the intensity of I1. That's the incoming short wave. And the way you enter formulas in Excel, because this is going to depend on these other variables, is you have to start off with an equal sign. So I'm going to say equals S naught. Now there's my box for S naught. I've already got it entered. So all you have to do in Excel is click on that field, and you see it says B2, B2. So that will that will enter 1367 when it goes to calculate this. The way you do multiply is by a star. And now I'm going to need a parentheses, 1 minus alpha. And what are you going to do for alpha? Well, I hope you're going to click on that box and close parentheses. And as I say, we've already taken care of the pi, we don't have to worry about that pi r squared. So when you're done with your formula like that, you press return. And you can see that I1 is 956. That's about that value, that dash curve right there. Okay, now if you want, give a shot at entering I2, which is the sigma t to the fourth times 4. Okay, here's how I think I should do that. I'm going to start off with an equal sign, as we do in Excel when you're entering a formula. And let's see, I need sigma. I've already got sigma there, so sigma and times is a star. T to the fourth, well, there's the temperature, but I need to raise it to the fourth power. And here's the syntax in Excel for doing that. You put this little hat and 4. So that's sigma t to the fourth. Now I still need this factor 4 right there, so that's just times 4. And I'm pretty happy with that, so I'm going to hit return. Fine, now the last little bit of this is I want an equation that describes the imbalance at the surface. Let's say, the imbalance would be that red amount divided minus the blue curve there. for whatever choice of the planet I want. So how do I do that? Well, I'm going to once again start with an equal sign and say equals I1 minus I2. Okay, and there we go. Now it's coming up and telling me that the imbalance at the surface is pretty big. It's like 594. That's because I'm down here at 200 Kelvin, and there's a lot more coming in than going off. If I had typed in 300 here, then that would have been something like here. I've got an imbalance in the other direction. Okay, now you could experiment and you could type in lots of different numbers here, but the last bit of this is to get Excel to solve that problem for you, which is to say, what is the best temperature to produce the smallest imbalance at the surface, close to zero. So the way you do that is you go to Solver, okay, and so Solver is going to ask for some fields, and one of them is the objective. What's our objective? Well, I want that box B9 to have a value of 0. So I have to click on this, and this is already 0. Now, how is Solver going to achieve that? Well, it's going to change some cells, and what it's going to change then is the temperature. So I'm just going to click in that box here and then click the temperature, $B5. Yep, that's what I want it to change. And I think we're good to go. Now we can just say solve it. And okay, it found a solution. Let's see if it was a good solution. Well, it found 254.86 degrees Kelvin, and that looks pretty good here. It's around 250. That's what I already knew the solution would be. And it said, and it's found an imbalance at the surface of, some pretty small number, 10 to the minus 4, and that's good. So we have used Solver to solve the problem of the atmosphere free radiative balance climate model.